Welcome to the second lecture of Part 4. In this lecture, we will be talking about logistic regression. Okay, let's start with a refresher. So here's a typical contingency table. We're interested in the association between a given exposure and a disease in the population. In order to calculate the relative risk, we're going to be comparing the risk of having the disease following exposure versus the risk of having disease following no exposure. In order to calculate the relative risk, it's going to be the number of subjects with disease who were exposed divided by the total number of subjects who were exposed. And this is the numerator divided by the number of subjects with disease who were not exposed divided by the total number of subjects who were not exposed. That's your relative risk. Now the odds ratio, you'll remember, is the probability of having the disease when exposed divided by the probability of not having the disease when exposed, and that's the odds of the numerator. And the denominator is going to be the probability of having disease when not exposed over the probability of not having the disease when not exposed. And that's your odds ratio. Now you'll see here that you can simplify when you're using probabilities to do that calculation. You can simplify and just use the number of subjects in each cell, which is A over B divided by C over D. In this slide, we're going to close the loop on something we mentioned earlier, which was an interesting property about the relative risk and the odds ratio, where with a decreasing prevalence of the disease in the population, the odds ratio will approach the relative risk. And you can see that here with the simple mathematical rearrangement of the calculation of the relative risk. You can break it down to this term here, where you have A times C plus A times D over A times C plus B times C. And interestingly, you can rearrange the odds ratio, which we had in the previous slide, of A over B over C over D, and you can have it as A times D over B times C, which, as you can see here, is the second half of this term for the relative risk. And as your disease, the prevalence of your disease decreases, A, and inevitably then A times C, is going to get smaller and smaller and smaller and more insignificant. And therefore, these terms, you can see the odds ratio will approach the relative risk as this term times C gets smaller. So this explains why when you have a very small, very low prevalence of disease in the population, that the relative risk and the odds ratio are very close. So here's an example with numbers. Sorry. If you look at here, we have our A and C. So the people in the population who have the disease and who are exposed, and the people in the population who had the disease and who were not exposed are quite small. So the prevalence is very low in the population for those who have the disease. In this case, when you calculate the relative risk, it's 5, and when you calculate the odds ratio, it's 5.04, which are very, very, very close. Okay, now what if we were to increase the prevalence of the disease in the population? So you can see here we still have a total of 10,000. The only thing is we've increased the number of people who have the disease and were exposed, and who have the disease and who were not exposed. And when we do the calculation, the relative risk is now 10 and the odds ratio is now 11. So they are no longer that close, relative to each other. And so this just shows how a relatively small increase in the prevalence of the population resulted in a fairly significant difference between the relative risk and the odds ratio. Okay, let's jump into an example. We're going to start off with our data statement here. That's going to build our data set. We have two categorical variables of interest, group and success. Group is for drug and placebo. Success is yes, no. We can print this data set if we wish. We then jump into proc-freq, which is to look at frequencies. We're asking for a two-way table between group and success. We're going to test the difference between proportions using chi-square, Fisher's exact, and we're going to ask for the expected values for each cell. Quick output at the beginning is just going to give you your frequencies here, which is just basically confirming what you've put in your data statement, which is going to be the different combinations between group and success, and then the number of subjects per combination. Here we have the two-way table, and you can see here on the bottom here is the expected frequencies, which have been listed here, and you'll note immediately that two of the cells have frequencies that are less than 5, and therefore we should be thinking about an exact calculation of the p-value. Okay, this slide is simply to show you that we can generate the same data set, but instead of grouping patients by combination of the two categorical variables, so the group variable and success yes no variable, we can actually list, as many data sets are created, each row represents one subject. In this case, there is no need down here in proc-freq to include the weight statement. Okay, so let's look at the outcome of our chi-square and Fisher's exact. So once again, this here on the left is just the two-way table giving our expected frequencies. And if we look over here, the first test to be listed is our chi-square. I'll also point out here the likelihood ratio chi-square, which we're going to talk about in a minute. We did talk previously about the continuity adjusted chi-square. Here it is. Remember that the continuity adjusted chi-square is often used when the numbers are small. We also have down here our Fisher's exact test, which is our exact p-value calculation, which you can see here for the two-sided, it's 0.0698. Okay, let's have a look at this new concept of the likelihood. Now, the likelihood is derived from the likelihood function, and the likelihood is a form of probability. Now, for example, what we've been dealing with is the probability of obtaining a given proportion. Now, in the modeling we've been doing is if we're given a hypothesized parameter of the model, what's the probability that the data we have observed resulted from this parameter? Now, the likelihood is conditional, and it actually looks at the data from the other way around, using a function to find an unknown parameter to maximize the probability that the data we observe comes from this parameter or results from this parameter. Now, once again, remember, you don't have to remember the calculations, just remember the concepts. You will remember from the previous slide the two-way table where we had 3 rows, one for placebo, one for drug, and of course the last row, which is the totals or the margin of the columns. Now, what we want is to derive from each of these rows the likelihoods. And so what is shown here are the calculations for the likelihoods. Now, it's simply the cell value divided by the row total to the power of the cell value. And we multiply this by the other cell value divided by the row total and to the power of the cell value. That is your likelihood. Now, likelihood 0 is your likelihood for the third row. Likelihood 1 is the likelihood for your first row, which is your drug, and likelihood 2 is the likelihood for your second row, which is placebo. Now, the likelihood ratio is then the likelihood 0, your margin, divided by the product of your likelihood 1 and 2, which is drug and placebo. Now, the negative log likelihood ratio is an interesting measure that is used to compare models. So in this case, the simpler model is in the numerator, which is your margin, and the more complex model, if you wish, is the denominator, which is the product of two likelihoods. Now, it so happens that the negative 2 log likelihood follows a chi-square distribution, and therefore we can calculate a p-value for the statistical significance as seen here in the SAS output. So when we compare the margin likelihood to the product of placebo and drug likelihoods, which assumes then that there's no difference, right? That's the null hypothesis. Our negative 2 log likelihood statistic is calculated to 5.3 with a p-value of 0.0213. Now, interestingly, SAS gives a chi-square test, the top line value of 5.05 with a p-value of 0.0246, which is very comparable. SAS also lists other chi-squares, namely an adjusted chi-square and a Mantel-Hansel chi-square. Now, these are simply different calculations to come to a similar conclusion. And as I've said before, you need to be aware of these as they are building blocks to more complex analyses down the road. Now, in the next slide, I will go over what SAS uses for this top line statistic it reports as chi-square, which is called the score test. What I will show you is that the chi-square distribution is the Z distribution squared, and that when you test the difference in proportions using likelihood ratios or with the Gaussian Z distribution, you get very similar results. Okay, this slide is showing the same calculations from the previous slide. However, what we're adding is a little comparison between the chi-square and the Z distributions. So same calculations for your likelihoods, same likelihood ratio, and same negative 2 likelihood ratio. What we show here is that if we simply take the square root of the negative 2 log likelihood ratio, which you will remember follows a chi-square distribution, we obtain a Z statistic that follows a Gaussian distribution or a normal distribution. We can then calculate the probability of obtaining a difference in proportions or one greater using both the negative 2 log likelihood ratio and our new Z statistic. And you can see that we obtain exactly the same p-values. Now, I'll point out that the p-value was derived looking at a chi-square distribution when we use the negative 2 log likelihood ratio, and we used the normal or the Gaussian distribution for when we use the Z statistic. Now this was simply to show you the relationship between the chi-square and the Z distributions, which, you know, the Z distribution is simply the square root of the chi-square distribution, and brings us to how SAS calculates the first listed chi-square test result from its output, and it uses the Z test with a Z statistic to estimate the binomial probability distribution, and this test is called the score test. Now you'll remember that the Z test was the difference in proportions divided by its standard error, and this is the pooled variance, if you remember, for proportions. When we do the calculation, the Z score is equal to 2.247, which is when it's squared is equal to 5.05. And you'll remember that this value was the value given by SAS in the first line for the chi-square statistic. And the associated p-value was 0.0246. So I'm just showing you here that whether you calculate it using the chi-square equation or you calculate it using the Z test equation, but then squaring it, you get to the same answer. And SAS uses this score test in order to provide you with a chi-square statistic and p-value. So one of the reasons it's interesting in order to do the score test is because then it allows us to use a correction factor for continuity that we've already covered with the Yates continuity correction factor. In this case, when you add the correction factor here, your calculation ends up with a smaller z-squared value and with a larger p-value, and these are reported in your output under the continuity adjusted chi-square. So finally, how do we get the exact p-value? So in this case, the p-value will be based on the number of possible combinations as or more extreme than the observed difference. So first we calculate the number of ways of getting each table. So I say each table because this is the table we observed. If you remember, this is drug and placebo. And these are two more tables that are more extreme than the one we observed. Don't forget keeping the same row totals. So if you calculate the number of combinations possible per row, and then the two rows together, you'll get 5,400 for our observed table, 450 and 10 for the two other tables. When you sum this, you get a total of 5,860 different combinations that would be as extreme or more extreme than the one we observed. So in order to get the p-value, we must look at the proportion of possible combinations as extreme or more extreme than the observed difference. In order to do that, we need to calculate the total number of 2 by 2 tables possible. So that will be the number of combinations we can get with a total of 20 because we are interested in the proportion of the first column, which is the yes column. The total is 11. So it would be 20 C11, which ends up with 167,960 different possible tables. Then to get the p-value, we simply take 2 times 5860. You remember that 5860 was the total from the previous slide. We take it 2 times because of the two-tailed p-value divided by the total number of combinations, and we get a p-value of 0.0698, which you'll remember was reported under the Fisher's exact test for two-sided probability in your output. Let's review. On the left, we have our 2 by 2 table. If we use the chi-square equation in order to calculate the chi-square statistic, we end up with 5.05 with a probability of 0.0246. We can also use the normal distribution in order to obtain the probability, and that is called the score test. And remember that the z-test squared is equivalent to the chi-square. We would get the same value and the same probability. If we use the likelihood function in order to derive the likelihoods of these 3 rows in our table and compare the ratio as our chi-square statistic, so actually the -2 log likelihood ratio as our chi-square statistic, we end up with 5.3 with a probability of 0.0213. Now, if we were using the score test, we can then continuity adjust that score test because it's a z-test, correct? And we end up with a value of 3.23 and a probability of 0.0722. And finally, if we were to calculate the exact p-value based on table probabilities, we end up with a two-sided probability of 0.0698. Now you're going to say, wow, why so many different ways of doing this? Well, I've explained earlier that these are building blocks that we need in order to do more complicated and robust analyses that we're going to cover shortly. But you'll see immediately here that our numbers here are quite small. And if this is the case, remember, I mentioned that you need to be aware of the expected cell counts. And for instance, if it's less than if 20% of your cells or more are less than 5, you should be considering the Fisher's exact test. And so in this case, the p-value you would go for or you would retain for your results is 0.0698. Now, interestingly, if you use the continuity adjusted chi-square, which I said the Yates correction, which when applied to the chi-square should be used when you are dealing with small numbers, you then end up with a probability of 0.0722, which is actually very close to the Fisher's exact test. It would not be a good idea for you guys to use the chi-square, the likelihood ratio chi-square in this case, because the p-values here would be biased. Okay, let's talk a little bit about proportions and probabilities. So you can see here that we have the same 2x2 table where we are looking for an association between our two categorical variables, our group variable where we have drug and control, and our outcome, which is success, yes, treatment successful, no, treatment not successful. And so if we assume that the difference between the observed proportions P1 and P2, where P1 is the number of successes versus the number of no successes within the drug group, and P2 is the number of successes versus the number of no successes in the control group, then the difference, if we assume that the difference between these proportions is due to chance, then we can replace these proportions with P naught and Q naught, which would be our hypothesized proportions. And you can see that these proportions are calculated based on the margins. So P naught being the total of yes divided by the total number of subjects in the study, and Q naught is simply 1 minus P naught. So then we can test the hypothesis that the probabilities, capital P1 and capital P2, are equal, that is P1 equals P2. So just to clarify a little bit that distinction between proportion and probability, probability tells you the likelihood of something happening, while proportion is just the comparison, of something measurable in quantities. Now, for instance, if you have a standard deck of cards, the proportion of diamonds in the deck is 1/4. And in this case, the probability to draw a diamond is also 1/4. So just as a reminder, once again, just because this is an important concept, we have our 2x2 table here. We have a drug in the first row, placebo in the second row, and our totals in the third row. Based on this table, we can then calculate using the likelihood function, our likelihoods for getting this proportion, so 7-3 with a total of 10, by using the likelihood function for drug, for placebo, and once again, for the total, which as we just covered, this is the margins, so this is going to act as our null hypothesis. Now I know you guys are, oh my God, wow, what's up with these equations? So you've already done it. So we just did it, 2-3 slides ago, and we just, calculated it by hand per row, and then we multiplied the two top rows and put them over your bottom row. This is just doing it all at once. So we're just doing the same calculation. Now here, what we're saying is under the null hypothesis, as we've stated, the probability P1 equals the probability P2. And then because of this, the combinatorial constants cancel out in this equation, and it leaves you with this more simple likelihood ratio equation. So how do we get to a test of significance? Well, the likelihood ratio test is therefore when using the likelihood ratio, so calculating the likelihood ratio, the -2 log likelihood ratio, turns out, has a chi-square probability distribution with a 1 degree of freedom. And so by using this distribution, we will be able to calculate the probability of obtaining a result as extreme or more extreme than the one we obtained. So this looks very familiar because we've already done it. We're just repeating it again, that we calculated, remember we calculated by hand the -2 log likelihood ratio using our 2x2 table, and it was given to us in SAS under the likelihood ratio chi-square. So you're thinking, finally these guys get to the logistic model. But we had to take you through the various chi-square calculations and methods of calculation in order to provide you with the building blocks to understand the logistic model. Because the chi-square has a limitation, and that is, though it's great to look at an association between two categorical variables, if you wanted to have as an outcome a binary variable or a categorical variable, but your independent variable was continuous, or you had more than one predictor or independent variable, then the chi-square can no longer be used. And so by considering the various building blocks we have for testing two proportions, one of them may be adaptable to this new challenge of ours of having multiple predictors or having continuous variables as predictors. So taking us back here to our data set, you'll see here it's exactly the same. Okay, in this case, we've chosen to build our data set by combining the levels of two variables and the count that you have for each of those combinations. So when we run proc logistic here, we call the same data set, but we use the weight statement because our data isn't one row per patient. We use a class variable for drug because, as you know, drug is a binary variable in this case for drug or placebo. Now the model, we call the model where we state this is the outcome, which is success, yes, no. Because it's a logistic model, the outcome has to be binary. And our independent variable is drug, as we've already assigned it as a categorical variable in class. Now the first output you get from running proc logistic is going to state what type of model, which is a binary logit, the number of response levels, which in this case is binary, so it's 2. And then it's going to give you, the number of observations read. In this case, it's 4 because there's only 4 combinations, but they're weighted. So there's the total sum of your subjects. And we are going to move on to the next half of the output. The second half of your results starts off with your model convergence status, which just means when you are dealing with maximum likelihoods, which proc logistic is, it is an iterative process in order to find the best parameters for your model, the best parameter estimates for your model. And so convergence just means that it was able to successfully find the best parameter estimates. Model fit statistics, we're going to talk about that a little bit later in the course. And so let's get down to what you guys are going to recognize, which is your test of hypothesis, your test of significance. In this case, we have 3, the likelihood ratio chi-square, which you'll recognize immediately, even has the same numbers, 5.3 with a probability of 0.0213. Your score test, which you'll recognize as well, 505 with a probability of 0.0246. This is all looking very familiar. The third one we haven't seen is the walled chi-square, and this one is derived from the logistic regression analysis itself, and we're not going to cover the calculation of this walled chi-square in this course because it's actually quite complicated, but SAS provides it for you in every proc logistic run. Okay, so let's just revisit the relative risk and the odds ratio. You're going to be looking at this 2x2 table many times just because we want to stress that we're using the exact same data for all of these analyses. And so here, once again, we're calculating the proportions. Remember little p1, little p2, so here they are. We then can calculate the odds for drug. So for cure yes on drug and for cure yes on placebo, there are your odds. So then if we look at the relative risk, you can remember it was the probability of yes on drug over the probability of yes on placebo. So it's 3.5. If we look at it the other way around, so the probability of yes on placebo versus the probability of a cure, so yes meaning a cure, on drug, then of course you get the inverse, 0.29. And we do the same thing with the odds ratio. It's going to be up here, 2.33 over 0.25, or the inverse, 0.25 over 2.33. The reason I'm stressing this is because depending on how you enter your data and depending on how your data is labeled, you're going to get the one or the other comparison. So be prepared for that. Okay, so let's continue looking at the PROC-logistic output. What it also gives you is the analysis of maximum likelihood estimates. So essentially what it's giving you is the parameter estimates to your model. As you know, you only have one independent variable in your model, which is drug. In this case, the reference is aspirin, which is drug, right? So that's versus placebo. You can see here it uses by default the Wald chi-square, which was shown in the previous output, previous slide for the output. And it also gives you your odds ratio estimate. So in this case, it's drug versus placebo. And you'll remember in the previous slide, we showed that comparison. And so the point estimate is 0.107 with the confidence limits of 0.014 to 0.838. And you'll remark here that it does not contain 1. Your confidence limits do not contain 1. And this means that there is a significant difference. And this is reflected by up here that the p-value is less than 0.05. Let's take a moment now to discuss a few properties of the logistic regression when using SAS. You'll remember a few slides ago when we were talking about the odds ratio that depending on the denominator, so the group in the denominator as your reference, your odds ratio can either be between 0 and 1 or greater than 1, or of course equal to 1 if they are both groups are the same. Now in SAS, when you run PROC-logistic, it will automatically assign you a reference, usually based on the label. And if you would prefer to have another group as your reference, you need to specify this. So I've done this here in this example. You remember in the previous slide, the point estimate for our odds ratio for group was less than 1. It was 0.1 something. And so, and that was, sorry, when we were using placebo as the reference. So what I've done here in the class statement for the drug variable, group variable, I've specified that I would like aspirin, so the drug, to be our reference. And you'll see here, down here in the odds ratio estimates, that the point estimate is now greater than 1. It's 9.333. And so you may be thinking, okay, well, how did SAS get this point estimate and where did it get it? So SAS obtains the point estimate from the estimate of your parameter for the drug variable. And interestingly, because logistic regression predicts log likelihoods, you need to exponentiate the estimate in order to get the odds ratio. So if you take the estimate of the parameter, 2.2336, and you exponentiate it, you get the odds ratio of 9.33, which is reported here. Now, just a word of caution. If you wish to calculate the odds ratio yourself from the estimates of your parameters, you need to make sure that you have specified here in your class statement that SAS uses what's called reference coding for categorical variables. And this is where for parameters, please use reference coding. So what this means is that inevitably, in order to perform regression, your variables have to be numeric. And so categorical variables are recoded. So if it's binary, they'll be recoded to a 0 and a 1. But by default, SAS uses a different type of coding, and I'm not going to go into detail as to why, but it uses effect coding. And so you need to request that SAS uses reference coding in order for you to be able to manually calculate the odds ratio. Does it mean you have to do this? No, of course not. Leave the default and then just look for the odds ratio down at the bottom in your odds ratio estimates box. Let's take a moment to review the outcome from ProcLogistic. Now, a few slides ago, we were talking about the log likelihood ratio and how you calculate it. And in model fit statistics, SAS calculates the -2 log likelihoods for you. In this case, the ratio is similar, but a little different in that the null hypothesized proportion, which was, if you remember, was the margin totals were used for P naught, and it was compared to the product of P1, P2, which were your proportions for your group, which was drug and placebo, so the calculation of the two log likelihoods for those two groups. And that was the ratio. And in this case, what we're doing is the hypothesized proportion is your intercept-only model, and then your intercept and covariates is your model. So in this case, we only have drug, which is our categorical variable of interest that we want to see if it's associated with the outcome. And when you take the ratio, or in this case, we're taking the difference because that's a property of logs, that a ratio of logs is equal to the difference of the logs. This yields the chi-square of the -2 log likelihood ratio, as you've seen before. And then you can test it to see what's the probability of obtaining a result as extreme or more extreme than this one by chance alone. Now, you'll see in the testing of global null hypothesis that there are 3 chi-squares that are given here, and I wouldn't worry about those. We've shown you how to calculate the likelihood ratio. We've shown you how to calculate the score test. And the wall test, as I explained briefly just before, is another chi-square that SAS prefers to use, and it's just because it's more robust, but it's complicated to calculate, so we're not going to go through how you calculate it. But all 3 of these are what they call asymptotically equivalent. So meaning that it's just a preference. So why do they keep listing them? Because just historically, different building blocks were used in order to come to this to logistic regression using ProcLogistic in SAS, and so they are, they continue to report them because everybody has a preference as to what they want to look for when testing the global null hypothesis. As we move down here, the type 3 analysis of effects is in effect your ANOVA, right? So remember your type 3 sums of squares. So this is an equivalent for providing you your type 3 sums of squares for drug. So this is the independent variable of interest. And what it provides you is whether or not this variable is significant in the model. So the parameter estimate of your variable is significant in the model. Your analysis of maximum likelihoods, this is where it provides you with the estimate of your parameter. And as we just talked about in the previous slide, this is where you would be able to, by taking the exponent of, if you exponentiate your estimate, you will get your odds ratio, which is down here. Okay, lastly, there are many ways to investigate or see if your model fits your data. The ones up here in the model fit statistics is just really the basics, the beginnings of seeing if your model fits your data. There are other ways to investigate if you have a very complicated model, or if your data is a bit tricky. Then there are other ways to assess the fit of your data, which you probably should do, but that's something you would do with a biostatistician, for example, or if you took interest, then you would learn about it in a more advanced course. Some of you may be thinking, where's the R-square? Because that's a useful measure to report, meaning the proportion, the percentage of the variability in the dependent variable that's accounted for by the model. In ProcLogistic, we don't have that. There have been some people that have come up with what's called a pseudo R-square, and there's also, you can look at accuracy of your model, which is what people tend to do and report that. That's something you can look at using the C statistic, but we don't have something specific like the R square in proc logistic. Now, before I leave this slide, I would just like to point out to you that if you look at the testing of global null hypothesis, all of the p-values for the 3 tests are significant, right? 0.02, 0.02, 0.03. But you'll remember using the exact same data set when we perform the chi-square, we mentioned that, oh, we should probably be using the adjustment for continuity in the chi-square, or we should be performing an exact calculation of the p-value because the sample size was so small and the expected values in your cells were less than 5, or depending on the rules. In this case, you can imagine that we've used a very simple data set in order to make it easy for you guys to follow and do the calculations by hand. So I would be very cautious here that just because we've used another procedure, proc logistic, and it gives you significant p-values, that doesn't mean that it's appropriate to use proc logistic with such a small sample size. And what would happen is someone might call you on it because they're going to look at the confidence limits of your odds ratio point estimate, and you're going to see they're extremely wide. And this is a sign that you have what's called scarcity in your data, or you have too small a data set. So what would I recommend in this case is I would definitely do what's called an exact calculation proc logistic. That's out of the scope of this course, but that's what I would do. You're wondering, oh, well, how would I avoid this? Well, very simply, the chances of this happening are small because before you set out to do your study, you would have performed a sample size calculation, which would have told you that the sample size that you have here would be too small for what you're interested in, and you would have collected more data to begin with. So what if we had more than one predictor? Now this is the reason we use proc logistic. And if we did, we can simply add them to our model. So for instance, here I'm adding sex and age alongside drug. I didn't add sex to the class statement because I've chosen to use 0, 1 as sex. If I had coded it as male-female, then I would have to add sex to the class statement. So when we look at the output, we're going to have an odds ratio for drug, which we've seen before and it makes sense. But we're also going to have an odds ratio for sex, and that also makes sense because these are 2 categorical variables, and we've seen using our 2x2 table how we can calculate the odds ratio. But how do we deal with that with a continuous variable? So then what we do with a continuous variable is the odds ratio is the odds ratio for every unit increase in age. So for every year, for instance, if year is the unit, for every year increase in age, the odds ratio for success, so the association of the 1 year increase in age with success, will be that odds ratio. Okay, so that brings us to the end of lecture 2 in part 4. That was a challenging lecture, so I would strongly advise you kind of review this one a few times. It's tricky, and not only that, but it's very important because proc logistic is a really great tool for medical statistics. Now, next up in lecture 3, we are going to discuss diagnostic accuracy.